He's Associate Professor in Ilan University and heading the group of Inorganic Chemistry and Nanomaterials for Energy Lab. He's an established scientist in many fields of electrochemical energy storage like flow batteries, fuel cells, electrolyzers, and many more. We look forward to your talk, Professor Zitoun.
Thank you, Rosie, and thank you for organizing this nice conference. I would like to be the host and share my screen, please.
You are allowed to share the screen.
Okay, thank you. So that's amazing to see people from Israel, Europe, and India and the US all together. And that's really a very nice initiative to do so. So I hope it will be also a tradition to do so in the future, even if we can travel. I will talk today about not exactly the title that was announced. I'm sorry for that, but I thought it was much more for this audience. It was much more informative to talk about battery and not exactly about electrolyzers and fuel cell. So I will talk mainly about hydrogen bromine redox flow batteries and how to push this technology forward to make it competitive to the incumbent, to the lithium-ion batteries. So this work was done by my group, and I would like to thank the group, the entire group. I will thank people during the talk also. And it was funded by ICL, by the European Union. And I would like to thank the collaboration with the group of Peter Fischer at Fraunhofer ICT in Finsal for the nice work on the bromine complexing agent that you will see. So this is the picture. I was born 45 years ago in 1975. So it was also about the time that Stan Whittingham was playing with the first lithium-ion batteries. And at that time, there was the need for about 6,000 terawatt-hour on the electricity side. And today it's about 4 times more. In 2050, it will be 2 times more. And so today, if you want to use a bit of storage, which is something that is needed, if you want to go for more renewable energy, and you would like to store about 1% of the annual consumption, you need 500 terawatt hours. So it means if we look only on the pumped hydro, we have like 5 terawatt hour, and we can't do much more about that. And if you look at batteries, we have this very, very small number. So we are completely out of the scope. And if you look at the mobility, it's about the same picture. 1975, you have about 0.3 billion cars. Today you have 1.4. Maybe with Corona it will go down. But even if we are keeping the same number of cars, we need much more of the batteries production that we have today. So that's why we see all these gigafactories, and that's very nice. But we also have to see that we need some more technologies. So as was said yesterday, it's not a choice that we have to do. We have to work on several technologies. So what can we do about alternative electrochemical storage? There are many things that can be done. What I would like to talk about today is about redox flow batteries. So the redox flow battery is about a battery that you flow the electrolyte, which is on one side the catalyte, on the other side the anolyte, and you flow it inside a stack that looks like the stack of a fuel cell. So it's like an hybrid between the fuel cell and the battery, or you can call it a regenerative fuel cell, a fuel cell that you would be able to charge and not only to discharge. And the good thing about it is that you can get some flexible design, so you can fix the power or fix the energy, because you can change the size of the tank, and that way you can change the energy that you can store. And usually the systems are very durable, and it should be based on very affordable elements. So that's the good side, the good points. The bad point is that you need to invest into the pumps because you need to flow. You need to also to think about not the crossover of the species from one side to the other. And in the case of bromine, it's really an headache. So if you're going to the point of the levelized cost of storage, which is, you want to put all the technologies together and to compare them. And at the end of the day, you want to know how much you have to pay for 1 kilowatt hour. So I've compared here two technologies, which are vanadium, the vanadium redox flow batteries, to the hydrogen bromine that I will talk about. So the main advantage of hydrogen bromine is the very high energy density, about 150 watt hour per liter, which is the practical one. And so in terms of the cost per kilowatt hour, you go down to $20 per kilowatt hour, just looking at the materials. But it's not only about materials, you need also to pay for everything. You need to pay for the cost of the tank, the pumps, the system, the pipes, the maintenance. And then you go to the cost, which is the cost of the capex, as it's called, which is about $95 per kilowatt hour. And finally, you have this number, which is about 3 cents per kilowatt hour. So if it was like that, I would sell a lot of these batteries today, because that's what people are looking for. These numbers are very good if you combine them with solar or with wind turbines. So that would be fantastic, but there are some challenges, which means problems. It's not the first time that it was done. So this is one of the sites that was installed by N-Storage, the company which is a spin-off of Tel Aviv University, the group of Emmanuel Pellet and Dina Golonitsky. And so they had a fantastic technologies that was scaled up by N-Storage. And you see here a site of about 1 megawatt hour that was installed in the south of France by the company Areva. And you can see here the hydrogen tank, and here the bromine tank. And in that large container, you have all the stack in the electronics. So that was done. And the point about doing that from Israel is that you have a lot of bromine in the Dead Sea. So here you have a nice picture of the Dead Sea. And this bromine is very abundant and cheap, and could be also strategic at some point. So let's go back to the redox flow batteries itself. So the low cost of bromine is one thing, but the really good thing about bromine is the good kinetics of reaction. You can go from tribromide to bromide without any catalyst. You just need carbon, and the reaction is very fast. On the other side, you need also to catalyze the reaction of hydrogen to proton to hydrogen. In that case, it should be a piece of cake, because there's a lot of materials doing that. We know about platinum, we know about iridium, we know about ruthenium. The problem is that these materials are pretty expensive and not abundant, and also they are very, very sensitive to corrosion, because we have some corrosion. So even if we can reach very high energy density, and the density can be very, very high if you had some complexants, up to 600 watt hour per liter, which is fantastic. In that case, you have a real issue with the corrosion of the catalyst. Why? Because when you're charging your battery, you have some protons that are transported from the anode to the cathode, and together they bring also some tribromide, okay? Because you have some association of the ions. So you have some electroosmosis of tribromine, and you have also some diffusion. And in that case, it means that you got a lot of bromide species crossing towards the platinum, the catalyst, and then it's corroded. Here you have the numbers that were calculated a few years ago. So the molar concentration is pretty high when you go to high current density, which is about 1 ampere per square centimeter. In that case, it could be 0.3 if you're a bit more conservative. On this charge, that's fine. It should be the reverse way. So the problem with bromine is that it's sticking on the platinum. You have here the black spots are the platinum atoms on the platinum 111 surface with some bromine add layer on top of it. So the bromine are the large green spheres. So the bromine is sticking to the surface of the platinum. And then when it's there, the platinum should do the reaction of the platinum, the dihydrogen splitting. So that would be the reaction that you have. And then you've got proton that is produced. But if you have some bromide on top of the platinum, even if you have this 0.5 coverage, then the hydrogen is sticking to the platinum, and then you don't have the second step, which is the dissociation, the Tafel stop step. So the reaction is blocked, and the catalyst is poisoned. So a few years ago with Dr. Gregory Gershinsky, we did the experiment. So what we did was soaking the platinum inside an electrolyte at 25 degrees, 0% state of charge, kind of low concentration, 3 molar. And what we've seen is a decrease of the platinum activity with time. So here you have the initial activity and then it goes down. And here we've plotted like that. And after a few hours, you don't have any more platinum in the on top of the layer. So the mechanism is like that. And if you go to soaking into a charged electrolyte, it's even worse than that. In a few minutes, 3 minutes, you just completely strip your platinum out, and it gives some bromidric platinic acid. So it was done also in cells, and in cells you have here the initial charge, discharge in day 1, and after a few days you can't discharge anymore your cell. So it's really an acute problem. So what we did to solve this issue was to design a membrane on top of the catalyst that could filter out the bromine species. So this is a very nice cartoon, and here you have a platinum, and on top of it you have a coating that is only porous to hydrogen and proton, and that is not allowing the diffusion of bromide. So it's done with polydopamine. We like polydopamine. It's a material that is very easy to synthesize. Usually muscles are using that just to stick on the stones in the sea, but you can also use it for other purposes. It was used for lots of application in electrochemistry already. So the polydopamine is giving you a nice coating on top of the catalyst. And if you're doing a thermal treatment to the coating, then you can simply decrease the size of the pores according to the temperature. We've done the kind of calibration curve, and now we know how to reduce the pores exactly the size that we want. And the size will be in between the radius of the bromine and the protons, or the hydrogen. And this is a TM picture, not the best one, that's showing that we have some coating on top of the platinum. And when you're doing that, so you still can see the hydrogen desorption. So this is the curve that you see in black for the platinum. When you're doing the coating here in blue, you still see the hydrogen on top of it. So it's porous to hydrogen. But if you're going to a very high temperature, in red, you close the pores and you don't see anymore. So you can really close the pores like that way. And when you're working with that type of coatings, then you have the same activity regarding less of the electrolyte. So you can work in a very mild electrolyte of perchloric acid, or in a very aggressive electrolyte of the charged electrolyte of hydrogen bromine, and the reaction is exactly the same. So we've done also some experiment to show that we don't have any influence on the diffusion constant of hydrogen, meaning that hydrogen is really going freely inside the pores of the coatings. And so what we've done is testing the electrodes after a few times, so after a few hours. So in black here, without coating, it's simply decreasing very fast. But when we have this coating, then it's pretty stable. The impedance also is very stable, showing that you don't have any film that is formed on the surface, mainly the bromide. So Kobi Saadi, he was part of the N storage and joined my team, and he was very successful to apply this technology to the cell. So this is the cell that we are using. And what we've done is simply comparing what's going on a platinum catalyst after a few cycles. So in red, this is the first cycle, and in black, after 57 cycles, and you see the decrease. And when we have this coated platinum catalyst, it's very stable for 100 cycles. And I will show you that it's also stable for even 1,000 cycles. So we did here for 420 cycles, and we don't have any fading of the capacity. The energy efficiency is about 80%, which is not too bad. And you see here in time, so after 27 days, this is the same. We don't run forever because we don't have the capacity to flow hydrogen forever in the lab for safety reasons. And about the crossover, so when you want to see if your catalyst can sustain, what you can do is simply stop the hydrogen flowing, and then you will have some of the liquid tribromide that is simply flowing to the catalyst. And so at the beginning of life, the coated platinum is even better than the platinum because there's no beginning of life. The beginning of life, it means that you already have some crossover. And after 2 hours that we force the bromine to go to the other side, then the platinum is really performing very bad. And the coating platinum is doing okay. So we did some publication about it and we are pretty happy. But we had some questions about the polymeric structure of the polydopamine. It's too complicated for us and we don't know how to address this issue. And it's really an open question. What is the structure? And when you don't know the structure, the problem is that you don't know how to make it better. So that was the XPS showing that after some time, if you don't have any coding, then you don't have any platinum anymore. So to do a rational design, Samuel Ardisti, which was a PhD student working in the lab in the Flow Camp, which is an IT and European consortium, he did some rational design. And what he said is that we need some proton conduction, we need some hydrogen permeability and chemical stability. So the solution were mainly oxide materials, or it could be also some carbon materials. And we would like to use simple techniques like wet chemistry or maybe atomic layer deposition that we heard about in the morning. So it did start with some simple Titania coding. So it did coding of Titania, which on top of platinum, this is platinum and this is Titania. So he did that. And by doing that, he increased the stability of the platinum by a very large factor that I don't know how to calculate because the platinum is really, the performance is going down very rapidly. And the Titania is still doing well after a few minutes into the electrolyte, the hot electrolyte, which is really a very, very aggressive test. And we, in collaboration with Malachi's lab, so we did some use of atomic layer deposition to coat some vanadium oxide. We don't see the vanadium oxide on top of the particle, maybe because it's too thin. We have to look into it. We do see some vanadium by XPS. The good thing about the vanadium is that we see some improvement, but not as good as the Titania as we did before. So we would like, I think that we have room to improve this technique. So we try to do another approach, which is to encapsulate the platinum inside carbon nanotubes. Carbon nanotubes are well known. They should also improve the loading of the catalyst because we can use a very small amount of platinum. And if we can encapsulate the platinum inside, then we would be able to also confine the reaction and block the bromine. So Victor Shoken did the nice cartoon that you see here, and also some of the experiment that you're going to see. But this work is mainly the work of Sam Ardisti. So we know that graphene on carbon nanotubes are pretty impenetrable to hydrogen. Okay, hydrogen just rebound on top of the graphene. So if you want to make it porous to hydrogen, you need to create some defect, or you can create some pores, and you can do it by oxidizing the carbon nanotubes. So that's what we did. And carbon nanotubes are very good because they are very small and they confine the size of the particles. They don't grow during the operation of the cell. And it has been demonstrated that you can get a rejection rate of about 98% by using this type of nanotubes for filtration. So it's very good for the dispersion of the catalyst, for the activity of the catalyst, and then you can modify your carbon nanotubes because that's really well known. You get a very nice toolbox for nanotubes today. So the idea is to put the platinum inside, and that we're gonna get some hydrogen diffusion, dissociation, and proton going out from the side. So we do that by this method. That is simply impregnation of the platinum salt inside the nanotubes. And what we get is the platinum that is inside the carbon nanotubes. And you can see here, it's really following the carbon nanotubes all the way. This is a very low mag image. So we see the nanotubes all over the place, inside the nanotubes and not outside. And we know that this is inside because we have here some image of EDX and we see the platinum inside the nanotube. We see that this is crystalline and the crystal is really following the walls of the nanotubes. Sometimes we have some defects. So these are the platinum atoms that we have in the nanotube. By AFM, we also prove that it's not on top of it because we have some phase and height image of the AFM. And what you can see that when we have one platinum here on the kink, then we don't see any difference on the height of the nanotubes. So it means that the platinum can't be on top or below, it has to be in. So we see that we have some charge transfer from the carbon nanotubes to the platinum, which could also help for the catalysis. The state of the platinum is platinum 0, platinum 2, so slightly oxidized on top. And the nice thing about these nanotubes is that they are very stable with time. So this is the platinum on carbon from Johnson Matthey that we use as a reference. And this is the platinum on the nanotubes. And this is very stable with this aggressive test. That's the best results that we had until today, better than the polydopamine and the Titania. So we also thought about using this kind of approach to modify the membrane, because that's also something that you can think about, not to protect the catalyst itself, but to block the bromine diffusion on the membrane. So what we did is to use some very simple separator and to put on top of it some graphene oxide. So this is the membrane that we got. This is a cross section of the membrane. It's about 4 micron thick. And the idea is that you've got a lot of layers of graphene oxide and the proton will go inside the pores, but the bromine will be blocked because you can measure, you can also control the interlayer species that you have between the layers. And it works. So what we did is to compare our standard membrane, which is a PDS silica that was developed by the group of Professor Pellet, and we compared it with graphene oxide on top of separator, and we got the same performance for the two. In terms of HFR, it's about the same, so we don't have a high impedance. So it seems that this system could work. Of course, we have still to look into the durability and the crossover of the bromine on very, very long term. That's what we are doing today. The last part of my talk will be about safety. So we know that bromine is a pretty volatile element. So especially if you work at 60 degrees, which is the best for the catalysis. So what you can do about it is to use some complexes, and the complexes are based on some Lewis acid, Lewis base interaction between the tribromine and some ammonium. So when you have that, here you can see without using some complexes, you have a lot of vapor pressure of the bromine, even if you're working with 2 molar, which is not the highest concentration and at room temperature. But if you're using some complexes, then you don't have any bromine vapor pressure, and it's safer, and then you don't have to invest into also a very expensive pipes and tanks and everything. So that's something that we work on. So you can see here some images of the one of the bromine complexing agent that we use based on pyridinium. So this is ethyl pyridinium. And based on the states of charge, you can see here that you've got 2 phases, and the second phase is the complex that you form. The good thing about these complexes is that they maintain the very high conductivity of the ionic conductivity of the electrolyte, and also they increase the energy density of your electrolyte. So they are doing really 2 good things for you. and they can go very high in terms of the energy density. Here you got the energy density for this salt, which is about 500 ampere hour per liter. It's about half of pure bromine. Okay, so that's something that is also one advantage.
2 more minutes.
Yep, thank you. But, and there's a big but that we published in Journal of Power Sources this year, is that when you try to cycle this kind of bromine complexing agent, they stick to the membrane. And so what we see here is the charge discharge with one of these ethylpyridinium. And we see here that we have some overpotential. And after some time, the overpotential is just going and going, and you can't cycle anymore. And so my conclusion is that we managed to do some bromide catalyst coding so that we can use still platinum with very, very low loading. We can go down, and I hope that we can go down to 0.05 milligram per square centimeter, which is about what PEM are doing today. We don't see any fading, and we can use bromine complexing agent for increasing the safety and the energy density. And with that, I thank you for your attention. I will try to answer the questions.
Thank you.
So I have 2 questions, so that's fine. How do you select membranes in redox flow cells? It is mainly site selective. So good point. How do you select membranes? You want the membrane to be mechanically stable. You want, to, of course, to get a lot of high potent conductivity. So it's about the same as what people are looking into PEM fuel cell, proton exchange membrane fuel cell. So you're testing the ion exchange capacity of your membrane, but also you have the membrane to be very highly selective to the types of ion that you're working with. So usually people are just picking into the catalog of proton exchange membrane fuel cell companies, and then they just doing some adaptation, some modification of the membrane. So that's what we've done, but also we've done our own chemistry. Second question, any redox couples that could generate higher voltage and also cost effective, at least above 3 volts for redox flow batteries? Okay, above 3 volts, then I'm not very confident with working with an aqueous solution. People have done some work with ionic liquids, or you can also work with water and salt maybe. But you have some couples that can provide 1.5 volts. So you can go to zinc bromide, for instance. You have other issues with zinc. I will not go into all the issues with it. But yes, you have other redox couples to go above, not to 3 volt, but 1.5 volt, yes. A question by Daniel Schroeder. What is your take on using organic solvent in redox flow batteries together with catalysts? Does this open new pathways for degradation and enhance the overall efficiency on the surface area of the electrode? So using organics, you have a lot of people working on organic couple in redox flow batteries. I guess you're thinking about using organic solvent, as I said before, like maybe ionic liquids or maybe a cheaper alternative to ionic liquids. So yes, that could be. I think that if we do that, we lose completely the advantage of the cost. And also we would have a lot of interaction with the catalyst. So you're perfectly right about that. And I think that, yeah, it's a good question. So yes, there should be some interaction.
There is one more question in the chat box by Sheikh Tirosh. You want me to read it?
Yes, please.
You could test TiO2 conformal coating that has been long time ago developed in our lab by Larissa Greenis. It is using the electrophoretic deposition. Actually, we can do a combined TiO2 and Al2O3 and much more. I think you can answer this in a chat box only.
Oh, the answer is yes.
Okay. Thank you for your talk. And now